This is where we ended last class. We talked about that Grignard reactions are a source of nucleophilic carbon. So whatever our organic portion of this molecule is, acts as a nucleophile, and we'll find out an electrophilic center and react with it. This is slightly electrophilic because it's bonded to an electronegative oxygen, so this would have a partial positive charge, this carbon. So would this one as well, but this will react with the least sterically hindered carbon in this case, in this oxirane. So this is kind of a special reaction. We react with oxiranes. Why does this reaction go so rapidly? And for instance, we would not see the same reaction occur. Oh, it's in my hand. With this kind of an ether. This is just a cyclic ether. This is a cyclic ether as well. Why do you suppose the Grignard reaction won't attack one of these carbons and open up this ring? Can anybody guess why that might be? This goes back to stuff you learned from last semester. Why is this reactive and this isn't? Ring strain, exactly right. There's a lot of ring strain because these bond angles are forced to be about 60 degrees. And what does a tetrahedral carbon bond angle want to be? 109.5, that's right. So there's a lot of ring strain in these compounds, and that's why these react with Grignard reagents. And these do not. And then last class we talked about reactions of Grignard reagents with carbonyl groups. Again, we have a source of nucleophilic carbon, and we have an electrophile. And the mechanism for all of these next reactions is going to be the same, whether we're reacting a Grignard reagent with an aldehyde, formaldehyde, a ketone, or an ester. The mechanism involves, we have the carbonyl group, and we have our electrophilic carbon, and we have some magnesium compound, and I'm going to write it like this, just okay. We also have now our nucleophilic carbon, okay? And we're going to move our electrons, and I'll point it right to the atom, okay? Where the electrons that are involved in this carbon-magnesium bond, which is very polar, some might argue ionic, are going to rearrange and become a bond between this carbon and this carbon. When we do that, we have to promote a pair of electrons up because carbon can only have 4 bonds. It already has 4 bonds. So if we put a new bond to carbon, we have to break another bond to carbon. In this instance, we break the carbon-oxygen pi bond, and we get this thing. Okay, and we have our magnesium, and our magnesium is going to associate, because it's a positively charged thing, it's going to associate with the negative charge on that oxygen. We have a salt right now. We have a magnesium alkoxide salt. And in fact, if you, hopefully you folks do some web searches on chemistry once in a while, and I found a site. Oops. Maybe I won't. Oh no, that's not where I wanted to go. It was right here. There we go. Okay, so in this particular site, they're a little bit more detailed in the mechanism. One of the things that some people will talk about a lot is that there will be an association between the carbonyl group and the magnesium even before the reaction starts, because we have kind of a metal center which likes to be stabilized by lone pairs of electrons, and particularly lone pairs of electrons on oxygen. So we actually get this pre-association before the reaction occurs, and that kind of sets things up, and we can push our arrows. They're pushing their arrows a little bit differently, but what we see at the end is we get this thing. They're showing a covalent bond. It's really very ionic in character, the magnesium-oxygen bond, and this thing would be better represented, as I have indicated, as a salt, okay? But it is tightly associated, especially, remember, Grignard reagents, we're doing these in ether. We can't have any water around because Grignards react with water. So we have what we call a tight ion pair. We do not get these things solvated in solution. Like if you throw sodium chloride in water, it disappears. It doesn't disappear, it gets solvated. It breaks up the crystal lattice. Well, here we won't get ether solvating these two things, particularly the anion. Ethers are very poor at solvating anions. So we get this tight ion pair. And then we take care of that in a separate reaction where we react with a little bit of acid. And at this point, we typically no longer bother with the inorganic portions of the molecule because they're just going to get solvated and taken away. We call this the workup, okay? And the workup is just the final reactions that we use to put some protons on some things that are negatively charged. Sometimes we'll remove protons from protonated things. We can have acidic workups, basic workups. The other thing we do is we make a lot of the junk soluble in one solvent, water, and a lot of the good stuff that we want will be soluble in an organic solvent, and we can separate it, clean it up. Okay? So, so that's our general mechanism. There we go. And we can do this reaction. This is the mechanism I just did on the board. Okay, so we typically do this reaction with aldehydes and ketones. We can make primary, secondary, or tertiary alcohols, just like we talked about last class. If we start off with formaldehyde, we're going to add this R group. We're basically putting a CH2OH onto that R group at the end. You can see here the blue sections are the new parts of this molecule. So we've added a CH2OH group to this R group. We've extended it by one carbon. We formed a carbon-carbon bond. We can do this reaction with an aldehyde. And with an aldehyde, we will get a secondary alcohol because the blue portions of the molecule, of the blue portion here, came from this, and the red portion came from here, and we see that we now have a secondary alcohol because there's two R groups on the carbon that contains the OH. And again, the mechanism always the same, the workup the same, although the workup becomes important here and here. Now you'll notice this is wrong, by the way. This should be NH4Cl. When we react a Grignard reagent with a ketone, we get a tertiary alcohol. And now I told you that it becomes important. It actually became important in the last one. With secondary alcohols, it's important as well. Why are we using, first of all, how many people recognize this as an acid? Okay, it's a source of H+, right? Because we have this thing. We can think of NH4 plus reacting to give us H plus NH3. This is our acid. This is our conjugate base. Okay, this is a source of H+. It's not a strong acid. It's a relatively mild acid. Can anybody think why we're using a relatively mild acid here. Now think about your products. Okay? In the workup, one of the things we got to think about is my product reactive? Can my product undergo any reactions that I don't want to happen? If I want this, I don't want it to get transformed into something else. What would happen if I used strong H2SO4? Does anybody remember?
Well, wouldn't the water would get protonated, the OH group would get protonated again, and then it would leave as water?
It could leave as water, and then what can happen to that carbocation? Especially if there's a CH2 group here.
Can it go back to a carbonyl?
Not really. But what is one of the reactions of alcohols? When we react alcohols, we have E1 and E2 reactions, right? E2 eliminations, we use a strong base and we form alkenes. E1 elimination, we start with an alcohol, we use a strong acid, and we get alkenes. So if we used a strong acid, our tertiary alcohol could get transformed into an alkene. We can get an E1 elimination. So we have to avoid E1 eliminations. Now this is also why it's important to come to class, right? Notice that that's not in the slides. It is in the textbook. Okay? So that's why we use something like NH4Cl, NH4 plus Cl. By the way, I can't fix these because the way the publisher provides them, it's all one item, and so the mistakes are not easily fixed. Okay, so our reaction with esters. Esters are a little bit different. What happens with esters and why are they different? Let's take a look at what happens. The first part of the reaction is the same. So in this case, we have an ester and we have some Grignard reagent. We have our nucleophilic carbon and our electrophilic carbon. We're going to react I'm going to put the electrons here. I don't always do this because but I will this time. Oops. Get this right. So we've added this to this molecule. We've formed what we call our tetrahedral intermediate. This is a specific kind of reaction which we will be revisiting with many different types of nucleophiles. It's called nucleophilic acyl substitution, the first step of this reaction. So, whenever we do a nucleophilic acyl substitution, we will be revisiting it. You don't need to know it right now. We're actually specifically going to look at that reaction in detail in a little bit. Okay, so we form this tetrahedral intermediate. Now, if we don't work this up, if we immediately put some acid there, we might think we could protonate that and get something that we would call a hemiacetal, which we'll learn in a little bit. But this thing actually can do something else, okay? It can reform its carbon-oxygen double bond, and then it's going to kick out the best leaving group. Carbon compounds are not good leaving groups, but oxygen compounds are. So it will kick that out. We've now made a ketone. Oops, this should be prime prime, and this will just be prime. Okay, and we've made a magnesium alkoxide salt. We've now made a ketone. Do ketones react with Grignard reagents? They do. Do we have Grignard reagent there? Yeah, we do. And in fact, one of the things that complicates this is that ketones react more quickly than esters, and aldehydes react even more quickly. So we've made a compound which will react with a Grignard, and in fact, it reacts fairly rapidly. So we can't even control this reaction by trying to put only one equivalent of a Grignard reagent in, because this thing will react faster. It will react, this thing then is reactive towards Grignards. It will react with another molecule of Grignard reagent. Okay, now we have a nice stable compound that's going to sit around and let everything else catch up. It's just going to sit there happily. It's precipitated out of solution, and it will wait until we add our workup and get to our final product, which is we just have to protonate this and we get the tertiary alcohol. And that's what they're showing here. This is the exact same mechanism I just did. And notice now we have a tertiary alcohol with 2 of the R double prime groups located on it, okay? So it is a convenient way to make a tertiary alcohol, so long as you want 2 of the R groups to be the same, is to start from an ester. Ooh. We can also react with CO2. Now I just want to CO2 is a special kind of carbonyl compound. It actually has 2 oxygens bonded to it, but it has this carbonyl functionality and then another oxygen bonded to it below, and we can react this to get this carboxylate. This is a convenient way to make carboxylic acids, and it's a convenient way to form a carbon-carbon bond as well. So you can see we can start off with this thing which we call bromobenzene, convert it to a Grignard reagent in the presence of CO2, make this carboxylate, and then just work it up with an acid. And here it doesn't matter what acid you work up with, you don't have to worry because the compound is nice and stable even under acidic conditions. Okay, I'm going to ask, that's a convenient place to end, I do believe. We have a couple of examples up here. These are just, they're all the same. We just now specifically have replaced our groups with something else. Here we have cyclohexyl magnesium bromide, which we would have made from the alkyl bromide. We react it with formaldehyde, and we work it up, and we end up getting a primary alcohol. We can react iodobenzene to get the Grignard compound, react that with formaldehyde. One of the things I do like about these slides is for most of the reactions that I can see, you can see where this part of the molecule came from because they've kept it blue. Okay, so you can see that framework. You can see that this came from this molecule, this portion of the molecule came from here. So that's kind of nice. It's nice mechanistically too. Finally, we react a ketone with a Grignard and we get a tertiary alcohol. Here's a specific example. And they then go on to make the ester example. This is a bit of a weird example, but we end up adding this isopropyl group twice. So here we have an isopropyl magnesium iodide, and we can add the isopropyl group to the carbonyl carbon. We get this species which is reactive and forms a ketone, and the ketone now reacts with another molecule of the Grignard to form our alkoxide salt, which we then work up and form our tertiary alcohol. We've taken this portion of the molecule and we've added 2 isopropyl groups to it. So I'm going to pass out the quizzes now.